So what we're going to be talking about today is panic and censorship in cosmology, JWST's data, and the fusion energy link. And you can tell by the length of the title that we have a lot to cover. So we'll get right into it. I'm Eric Lerner. I'm President and Chief Scientist of LPB Fusion. So why is there panic in cosmology? Why are papers coming out after the JWST, the James Webb Space Telescope, has released data that caused people to write a title with panic right in the headline, panic at the disks? So what's going on here? And what does it have to do with censorship and with the fusion energy effort? So in order to understand what's going on, we have to take a step back. And this presentation is going to be in three parts. First part, we're going to describe the situation prior to July 12th, when JWST started releasing its data. Then we're going to take a break and we're going to have a couple of questions, and then we're going to take a look at what is the meaning of the JWST data, the first 2 weeks of it, and what does that imply for the Big Bang hypothesis. We'll then take another break for questions and then do the final section, which is the Big Bang didn't happen. What is the nature of universal or cosmic evolution? And what is the very real connection between that and the fusion energy effort? So let's start with the Big Bang. When we talk about the Big Bang, we're actually talking about a theory that has had many lives. It started in 1931 when Lemaitre first proposed as a reason for the Hubble relationship, which had just been discovered, that the universe was expanding from what he called a primeval atom. This was before the coining of the term Big Bang. And he gave as the primary observational evidence for that cosmic rays, which had also recently been discovered. And he said nothing in the present day universe could create these cosmic rays with such high energy. Well, not many people actually paid attention to this. And in 1935, Hannes Alfvén, who we'll get back to later, he showed that the magnetic fields that are reasonably expected to exist on a stellar and galactic scale, and which were later observed, could accelerate these cosmic rays using basically mechanisms that were very similar to what accelerators, which had been invented recently as well, we're using here on Earth. So that sort of ended that first phase of the theory. Now, in 1946, in the wake of the Manhattan Project, which George Gamow participated in, the second Big Bang was born. And Gamow said the Big Bang was just like a big atomic explosion. And it created all the elements that we and the planets and the stars are now composed of. He had a lot of trouble working out the details. And only a few years later, 1957, Boyle, the Burbages, Fowler came out with a huge paper which showed in great detail how nuclear fusion and other reactions in stars that existed in the present day universe could create all the elements from an initial population of hydrogen. So that was sort of the second cycle. But again, the theory rose from the dead in 1965 when Peebles and Dickey pointed to the cosmic microwave background, which had just been discovered, and said, this is the diffuse echo of the Big Bang. There's nothing that could have produced this radiation, even though this radiation was at a little below 3 degrees Kelvin, and this was supposedly an echo of an explosion that occurred at a trillion of degrees Kelvin. So it was a bit of a stretch, but that was the basic idea, and that was the evidence. And this time it was widely accepted by the media, by other cosmologists, and by the public. So this ran into trouble in the 1970s because people like Alan Guth and others who looked at this theory realized that it did not predict a smooth microwave background. Because if you looked at parts of the sky that were more than a few degrees separated, there would not have been time during the Big Bang for these parts of the universe to have actually come into equilibrium because they would have been limited by the speed of light. So what the theory actually predicted was a crazy quilt sky in which the temperatures would be all over the place. So that wasn't what was observed. So that was a big crisis. And the crisis was actually not very much discussed in the literature until Guth came up with an explanation, or a so-called explanation, which was inflation. And this was, by the way, a period of great monetary inflation, economic inflation. So his idea was that there was this new force, the inflationary force, which existed only at the beginning of the universe, and for a fraction of a second expanded the universe so rapidly that a tiny part of the universe that had already, in this fraction of a trillionth of a second, come to equilibrium, was expanded over the entire sky. So there was another problem. Inflation demanded that the universe be what is called four-dimensional flat, which meant that there was a certain predicted amount of total matter. That amount of matter was both extremely high compared with the amount we observed, and also was completely in conflict with the density of matter that was required by Big Bang nucleosynthesis, which was a theory developed during this time to predict the abundance of light elements, hydrogen, of helium, deuterium, and lithium. So you had to have another hypothesis, which was dark matter, non-baryonic matter, matter that's completely different from anything that we have in the universe today. So there was no more additional evidence, but there were two more additional hypotheses. Well, this went along until the end of the century, of the last century, when other problems emerged. Observations of what the Hubble relationship actually was, which in the Big Bang theory predicts the age of the universe, ended up with a dark matter prediction of about 8 billion years. And there was already abundant evidence that the galaxy we live in, the Milky Way, was a great deal older than that, 14, 15, 16 billion years old. So that really didn't work. In addition, the measurements of supernova brightness, which were being used as a gauge of what the true Hubble relationship was, they were coming out wronger and wronger as you moved out. It looked like the Hubble constant would have to be different at different z redshifts. So the only way that could be put together is by a third new hypothesis, of course, everybody has heard of, which is the famous dark energy. So this was, again, a new force, no evidence for it on Earth, not even possible to derive evidence for it on Earth, which was pushing the universe apart just fast enough to counter the dark matter. So that's where we were when we entered the 21st century. But problems began to accumulate. So this is a curve that I developed based on the published literature of the predictions of the Big Bang in different data sets that were deemed correct in the published literature and those who were deemed wrong. We'll get to the green line later. But the number of predictions that were deemed right was that blue line. And the number that were wrong was the red line. And what you see is things seem to be going quite well in the first decade of the 21st century, which is the first decade of the dark energy theory, a lambda CDM theory, as they call it. But in the second decade, things really started to fall apart. There were more and more contradictions until in 2014, there were more contradictions than correct predictions. And today, there are almost no correct predictions. So let me give you just a few examples of the main wrong predictions. I don't have time to go into all of them. Lithium abundance. Lithium is one of the light elements that's predicted that if there was a hot, dense period for the universe, lithium must have been produced in a certain amount. And those are the red lines, is the parts per billion of lithium versus hydrogen. That's the prediction. We can measure lithium spectroscopically in old stars in our own galaxy. And those are the data points. And this is plotted against the abundance of iron. Iron is produced only by supernova. So the less abundance of iron, the fewer supernovae have exploded in the history of our own Milky Way galaxy. So presumably the older and purer the star. And you see that the trend is downward towards zero. And the best pure element stars are about a factor of 20 below Big Bang predictions, way off. Helium, much more abundant element, a quarter of the universe is helium. We can determine from nearby stars by looking at their luminosity, their radius, their temperatures, how much helium there is in these stars. And by two different ways of measuring it, these measurements back in 2010 show that the nearby stars, as they had less heavy elements, unfortunately, this is again the letter Z, but it's not referring to redshift, it's referring to abundance of heavy elements called metallicity. As those get lower, the amount of helium drops below the predictions of the Big Bang, which is this red line here, and goes down to about 11%, which is half the predictions. So again, a gross contradiction, they call this the helium problem. There's no solution to this problem. It's a gross contradiction. 14 billion years sounds like a long time to us, but it is not long enough to form the largest structures we see in the universe. In the time available since the Big Bang, the theory is very firm in predicting you can only get up to objects that are about 150 megaparsecs in radius. That's 450 roughly million light years in radius. If we look out into the universe with these deep surveys like the Cosmos survey, it's the name in the survey, we see that there are concentrations of superclusters of galaxies that stretch over gigaparsecs, thousands of millions of parsecs. That's simply impossible. These objects are obviously hundreds of billions of years old. They're much older than the period since the Big Bang. And this is not something I say. If you go back to Joseph Silk, one of the pioneers of the Big Bang theory, over 30 years ago, he said, if you found objects that extended over 1,000 megaparsecs, you would have to seriously question the Big Bang theory. Well, those objects exist and we do question them. We'll get into why more people aren't questioning it later. The inflationary theory doesn't make many predictions, but it does predict that these small fluctuations in the intensity of the cosmic microwave background should be totally random, Gaussian, over the surface of the sky. While it's been known for years that they're not random, this is a map of these fluctuations. They're quite small. This is hundreds, parts per million. But if you look at the hotter areas, the red areas versus cool areas, there's obviously a pattern. And there's a pattern of various sorts at various large scales. They're definitely not Gaussian. There's a complete contradiction. The contradiction you've probably been hearing about, the crisis in cosmology contradiction, is that by fitting predictions, fitting formulas to these tiny fluctuations, the Big Bang theory predicts the actual value of the Hubble constant, the Hubble relationship between luminosity and redshift. The lower curve shows those predictions from better and better data of the cosmic microwave background. And the upper curve shows the measurements from many data sources, including the supernova measurements. And as you can see, they're now in gross conflict, and this conflict is getting worse. And finally, we get to a contradiction that I and my colleagues, Riccardo Scarpa, who's here today, and Renato Falama, developed over the past decade, which is surface brightness. So if the universe is expanding, no matter what the theory, there's a strange optical illusion, which after a certain distance, objects appear larger on the sky with increasing distance rather than smaller as they do in ordinary non-expanding space. So what that means is that the surface brightness of objects, that is their apparent luminosity on the sky, divided by their apparent surface area on the sky, gets dimmer and dimmer very rapidly with high redshift. In the real space that we live in, local space, non-expanding space, surface brightness is always a constant. If an object is twice as far away, its luminosity goes down by a factor of 4, the distance squared, and its area goes down by a factor of 4, the distance squared. So the ratio of those two numbers is constant. Well, we used Galex and Hubble data to go from low redshift, essentially 0 redshift, all the way out to redshift 6. And we found that the surface brightness was dead constant, just as is predicted by the non-expanding universe theory, using only one assumption, which is that the relationship of distance to redshift is linear at all redshifts, just as we know observationally it is at low redshifts. This red line is the prediction of surface brightness of the Big Bang theory or any expanding universe theory, and it's completely wrong. The only way they square this circle is by saying, and we'll get into this in the next section, that these distant galaxies must have been very, very tiny and very, very bright surface brightness, so that the dimming that they don't observe just neatly compensated for this extreme brightness and extreme small size. How did they grow up? Well, they smashed into each other. They had collisions, and somehow they expanded many-fold to the present galaxies. That's the story. So if we look at all of these data sets, and I said I don't have time to go into all of them, there are 16 clear contradictions. And there's only one remaining right prediction, which is the abundance of deuterium is correctly, accurately predicted from Big Bang nucleosynthesis. So that is a terrible record for a theory that claims to be well validated. And this is not just us speaking. Again, Joseph Silk and colleagues says the inconsistency between different desperate observed properties of the universe introduces a problem for modern cosmology. Flat lambda CDM, which remember is the current version, the fifth version of Big Bang hypothesis, does not seem any longer to provide a suitable candidate for concordance cosmology. In other words, it's wrong. Well, Ricardo had the idea that we should predict what James Webb Telescope was going to find. And he convinced me that this was a good idea. So we wrote this paper together. Will the LCDM cosmology survive the James Webb Telescope? Now, I had been working on general papers that took all of this evidence against the Big Bang hypothesis and for the contrary hypothesis that the Big Bang never happened. And I had put them together into two large papers, which are the lower ones. And we submitted them to big journals, such as the monthly notices of the Royal Astronomical Society, MENRAS. And both of us had been published by MENRAS before, including for papers that were pointing out some of these contradictions. But they refused to publish them. And it's not just the reviewers didn't like them. It's, in the case of the first one, it never got to a reviewer. In the case of the second one, the reviewer okayed it, but the science editor said no. And what happened was the science editor, who was anonymous, in the case of the first paper said, plainly the answer is no one knows since there is yet no data. The authors claim that they already know. In other words, they predict what the JWST data will be is plainly unscientific. So here the science editor is actually throwing out the core of the scientific method, the core of the thing that makes science extremely useful to humanity, which is the ability to predict observations before they occur. In the case of my papers, the anonymous MENRAS editor said, well, maybe some paper would, maybe some publication would publish an overview of what's wrong with the standard Big Bang, but MENRAS will not. In other words, they flatly refused to publish any paper that said what my papers concluded. Well, we went to arXiv, because arXiv is supposedly an open archive of all physical sciences papers. And they're not supposed to peer review it. And guess what? They refused to. Now, they didn't even give an answer because they used form letters. So we said this was censorship. And 24 scientists agreed with us and signed a petition of protest. And that's basically where we came up to now. Now, what predictions were they censoring? Well, there were a number, but the two most significant ones at this time for this presentation is, guess what? We said the universe was going to continue to be not expanding, and therefore surface brightness was going to continue to be constant, and the angular radius would decline as 1 over z. Second of all, we said older galaxies will exist in this distant universe. So we foresee that elliptical galaxies, which are the older, more settled galaxies after star formation has ended, would still be visible. So with that, I will conclude this section and then open it up for a couple of comments and questions. Ricardo, do you want to add anything?
Hi, Eric. Nice presentation. Very easy to follow and simple and clear. Well, the only thing I want to add is that it is a very interesting moment in the history of astrophysics. I have the feeling that within a few years, the James Webb Space Telescope will completely demolish our view of the universe, which is based on the lambda CDM and the Big Bang theory, and it will send us back 100 years, and we will have to restart and try to understand the universe, but looking to it from a different point of view.
Right.
And obviously, there are extremely important consequences to this, because if dark matter is not needed in cosmology, then it will be abandoned completely, and a new theory of gravity will have to emerge. So the impact of the James Webb is going to be tremendous, either in both in astronomy and physics.
Right. I certainly agree. All right, I'm going to take 2 questions. Let me see how we're going to do this, because there are a lot of people on. People will have to raise their hands with the little hand raise thing that's at the bottom, where you can applaud or something. You can raise your hand. Right, I don't see any hands. Okay, so why don't you just, if somebody wants to speak, unmute yourself. Any questions?
Hi, Eric. Hi, it's David Wexler.
Hi,
Very
Dave.
interesting talk. Thank you. I mean, it's very compelling what you're saying, but how is it possible? How is it possible in the world of cosmology, with the expert physicists working on this, that other people aren't seeing this?
We'll get to that. I'm not answering that question now. We'll get to that in part 3. So, but yeah, we'll talk about that. I will give a hint of the answer. It's a phenomena I call the Emperor's New Clothes effect. So that'll give you an idea. One more question, and then we're going to go on to what James Webb Space Telescope has told us so far. Anyone else, just unmute yourself. Okay. In that case, we're going to go on, and I'm going to put you back. Okay, so one of the first things that James Webb Space Telescope has discovered, or the data from that, the telescope hasn't made any discoveries itself, it's not smart enough, but what the data from the telescope has shown us is there are a lot of bright high Z galaxies. And I've been following this on the, excuse me, I have to minimize something. There we go. I've been following this on the archive, and people are publishing straight off, even within the first 2 weeks of this data being available, because they were pretty much ready to go. And as of last night, there were 20 galaxies with a Z more than 7 that have been discovered. And this galaxy is one of the most extraordinary, which is carefully measured, which, as they say, is JHC 2. Well, what about surface brightness? Well, let's map it out. So using the observations in the papers that have been published just in these last 2 weeks, I have plotted out the Hubble results that Ricardo and Renato and I had developed from the Hubble Space Telescope, which are these dots at less than 5Z in each of these diagrams, and compared them with the new data from JWST. And if you look at the radius, so this is the radius assuming that we were in a non-expanding universe and that redshift scales as distance. What we see is that the range of galaxy radii is very comparable. Now, these are cut off to be only very bright galaxies, because obviously the brighter the galaxies, the bigger it is. So these are galaxies that in astronomer speak have absolute luminosities brighter than -20. And take it from me, I look, there is no correlation. There is no tendency for these galaxies to be larger. And there is no tendency for the surface brightness to grow. There's a bit of an apparent slope, but that is purely apparent. We aren't observing the galaxies that at this distance would be in this section, because they would be galaxies that would be less than 10 kiloparsecs in radius. Most of them would be unresolved even by JWST. We will be able to see them because they'll stand out, that their spectra will tell us they're not stars, they're galaxies, and we'll be able to fill in the blank. But even with this data, we can see the prediction of the surface brightness is valid out to a redshift of, approximately 12. There's one that's even reported out to 16. If we assume the Big Bang hypothesis, we get a very different picture. We get a picture that the surface brightness continues to increase to wholly unphysical levels. Again, this is the surface brightness, assuming that we have to put in this correction for this optical illusion, which would not exist if the universe were not expanded. So it's a double negative, as it were. The red line is the brightest galaxies in the local universe. So these are the galaxies that have the brightest surface galaxy of any we can see nearby. Unfortunately, astronomers again have this habit of making magnitudes smaller, meaning brightness is bigger. So as we go down, we're getting brighter and brighter. And this super galaxy down here is hundreds of times the surface brightness of any galaxy in our local universe. So let's look at that super galaxy. I call it a Mighty Mouse galaxy because it would be extremely bright, far brighter than our Milky Way galaxy, but extremely tiny, very much like Mighty Mouse. So let's compare this galaxy, GHZ2, with the Big Bang theory on the right and no Big Bang on the left. If no Big Bang, this is a pretty typical, very bright, very star-forming galaxy. 6 kiloparsecs in radius. It's a little smaller, but not much smaller than the Milky Way. Very luminous, with a surface brightness near but below the brightest ones that we see. So it's within the range of the brightest ones we see nearby. And the volume brightness, so the luminosity per unit volume, is again within the range we see. Well, if we take the Big Bang Mighty Mouse assumptions, this galaxy is hundreds of times smaller in radius than our Milky Way galaxy. Has approximately the same luminosity, either assumption. So very luminous, a tiny volume, hundreds of times the surface brightness of any galaxy we see around us, and thousands of times the volume brightness. Well, how would such a mighty mouse grow into a regular galaxy? Well, the story is just exactly like you take a super toy truck. Now, this is a super toy truck because even though it's only an inch across, it has the same mass as a great big F-150, pickup truck. Same mass, 100 times smaller. How does it grow? Well, the traffic accidents. So traffic accidents occur between these super toy cars, and somehow they sort of get smeared out to a great big pickup truck. Well, you would expect a few dents, and that's where we get the panic, because JWST can look back and look at galaxies far away at high Z, where they should be undergoing many, many mergers, because they're quite tiny according to the Big Bang. And why is there panic at the disk? Because what does JWST? This is a very much blown up section of that iconic image Mr. Biden showed to everybody. What we see is very beautiful, smooth disk galaxies. And if we blow it up a little further, we can see, wow, a tiny, very nice spiral galaxy. You see the little spiral arms. Little only from the Big Bang. Actually, this galaxy is just the same size as the galaxies today. So the reason that this caused panic, or the authors expected it to produce panic in others, was that almost all of the galaxies look like this. And what did the authors say? There were 10 times more disk galaxies, that's another word for spiral galaxies, than we had thought. 10 times as many as they had thought, not we. This implies disk galaxies have existed in large numbers for quite a significant amount of time, quite an understatement. They have remained the same morphology, which obviously couldn't happen if they were colliding all the time. This would challenge our ideas about mergers being a very common process. In other words, in astronomer underspeak, it would obliterate that hypothesis. So that's why we've got a big problem just in the first 2 weeks for Big Bang hypothesis, because you've got these little tiny galaxies, even littler, even tinier, with no ability to collide together, because at all redshifts, they're nice, smooth, highly structured, but obviously non-colliding galaxies. And the galaxies that do collide, the peculiar galaxies, are a small minority. So that's big problem number one. But I'm sorry, I skipped over. Big problem number two, a bonus problem, is they see elliptical galaxies. Now you can tell the difference between elliptical and spiral galaxies, not only by the shape of their light profiles. It's very distinct, but also by their spectrum. Elliptical galaxies are obviously older. They're bright, young, hot blue stars have burned out, so you have more red stars. They are redder in color. Well, here's a galaxy, ID 3602, at Z equals 9. The Big Bang age of the universe is supposed to be 540 mega years, but the spectrum is very red. So it goes up, and the observed spectrum is the red line. They fit it with this blue model, which would tell the modeled age of that galaxy, but the authors don't share it. And the reason is, that I suspect that they don't share it, is that they don't want to say this galaxy is older than the Big Bang. But if we look at models of a billion-year-old galaxy, the blue line, it's a reasonably good fit. And even a 13 billion years old galaxy, it's not a bad fit. A 500 million years old galaxy is a bad fit and would be ruled out by this data. So in this galaxy, and it turns out in a couple of galaxies that were reported just yesterday, the age as reported by the stellar spectra is older than the age of the universe. So again, complete impossibility, if complete contradiction with the Big Bang. So in 4 weeks, in 2 weeks, 4 contradictions. Surface brightness and radius are constant. The impossible Mighty Mouse galaxy, no mergers to grow the Mighty Mouse galaxies, and an elliptical galaxy, in fact, 3, older than the Big Bang. My conclusion, which I published 30 years ago, is that the Big Bang never happened. So let's break here again and talk about these results from the James Webb Telescope. So again, if there aren't too many of you, I think just unmute yourself. Questions, comments?
Hi, Eric. This is Douglas Lund Yates. I very much admire your book. I read it, the first edition, back in 91, 92. In fact, I have it on the table here. What do you think the crux of the matter is? Is it the doubt of the Hubble constant, or the reason for the Hubble constant? Could it be another reason for the redshift?
Well, as I say, I'll get into that in the
that?
final section of the talk. But, you know, if we get into why are so few cosmologists and astronomers questioning the Big Bang hypothesis itself, our experience indicates why. And it is the Emperor's New Clothes. I mean, the Emperor's New Clothes fairy tale, which did reflect social reality, was that if you couldn't see the Emperor's New Clothes, you were unfit for your job and you should be fired. Well, that's the situation that has developed in cosmology today. Funding for this work comes from a very few concentrated government sources. The committees that give out those funds have been dominated for decades by theorists who have devoted their entire careers to developing the Big Bang. Nobody likes to be proven wrong. If you ask for funding for things that question the Big Bang, you're not going to get funded. Now, up until recently, if you could do the work on your own funds as a sidelight, then you could get published. And, you know, I published some of these results that we're discussing in MENRAS as recently as 2018. But when the crisis in cosmology became publicized, when you had these two groups of cosmologists saying the Hubble constant is not what the theory predicts it to be, I think, I don't say that I have this on high authority, but it seems they circled the wagons and they stopped allowing the publication of anything that says the Big Bang never happened or the theory is flat out wrong. So that's what's happening now. It's not that people don't think the theory is wrong. It's that they can't say it, that these people are putting their hand over the mouth of the child who's saying, hey, the emperor is naked. So that's what has to be broken through. I think that in the coming weeks and months, it will be broken through and the mass media will start covering this debate and the censorship as well.
Hey, Eric.
Okay, let me stop sharing the screen for a minute and then I can see whether anybody else wants to. We'll have one more question or comment before we go into the final.
I just wanted to reiterate the question this guy was asking about, is there maybe a different interpretation to the redshift?
Right.
Like, are they just getting the redshift wrong? Is that the problem?
No, I think there's a lot more wrong. But let me answer that in the final part of the presentation, and then we should have plenty of time. Actually, I forgot to ask at the beginning. I assumed somebody would told me, is there anyone here who wants to defend the Big Bang hypothesis? Because I did ask the leading proponents of that hypothesis to debate me, but none of them responded. Does anyone want to have some time to defend the Big Bang hypothesis? Yes. We will get to that. I am convinced we will get to a debate, but not tonight. Okay, so let me go back to the share screen. Okay. What are the basic processes in cosmic evolution? If you eliminate the Big Bang, you throw out inflation, throw out dark energy, you throw out dark matter. Can we explain cosmic evolution in terms of processes that we understand and can test here on Earth and in the solar system within reach of our spacecraft, which are part of our experimental apparatus? We find we can, and there are certain key processes that are involved in cosmic evolution. First of all, there are processes dealing with the forces of electromagnetism. Plasma processes dealing with, as I say, plasma where electrons are stripped off of atoms and are free to move. And I'll get into some of these processes in just a second. Obviously, gravitation is extremely important at large scales and at small scales. And finally, the universe has been shaped by nuclear reactions, especially fusion reactions that have built up the elements. So very briefly, let's go through some of these concepts that are important in understanding the real evolution of the cosmos, and unfortunately are basically ignored in both the education of the average astrophysicist and in most astrophysical work. Not all, most. In doing so, we are going to use a basic method that is enunciated here by Hannes Alfvén, the pioneer of plasma physics, 1970 Nobel laureate in physics. To try to write a grand cosmical drama leads necessarily to myth. To try to let knowledge substitute ignorance in increasingly large areas of space and time is science. So we're not trying to say, oh, we can write a better origin of the universe story by saying what our equations tell us the universe must have been like, which is what the dominant theory of cosmology is. No, we work outward from our knowledge of the universe here on Earth to the solar system and outward from there. and of course, going backwards at the same time in time. First basic principle that has shaped the universe is the pinch effect, discovered by Ampere 2 centuries ago. Pinch effect occurs when two electric currents are traveling in the same direction. The magnetic fields created by those currents create forces which draw those currents together. So there's an attractive force created by magnetic fields created by currents. So that means that currents moving in the same direction attract each other, in the opposite direction repel each other. And this can be proven, including with recent simulations, to mean that small random currents in a plasma at any scale tend to grow to be bigger and bigger organized currents. Second phenomena, anisotropic conductivity, magnetized plasma. This means that in a plasma that is not terribly dense, not like the density of stars, the magnetic field is sufficiently strong that particles, either electrons or ions, will travel in circles around magnetic field direction and only occasionally collide to move in a direction perpendicular to the field. That means even if the electric field is almost perpendicular to the magnetic field, the current will move in the direction of the magnetic field, not in the direction of the electric field. It's a phenomenon we've studied a great deal in fusion plasmas. It's dominant throughout the universe, and unfortunately is not that much understood. This was one of Alfvén's pet peeves, which he actually talked about in his Nobel acceptance speech, that people were misunderstanding certain concepts he had developed, and therefore were dealing with what he called pseudoplasmas, not real plasmas as they exist in the universe. If you put these two phenomena together, the pinch effect and anisotropic conductivity, you get force-free plasma vortex filaments as a key structure in the universe. These are filaments that are so arranged that at all points, the current is moving along the magnetic field direction. So they have a very tight screw spiral along the outside, a looser spiral towards the center, and then current moving straight along the axis. This is what we see everywhere in the universe, is fractal hierarchies of these vortex filaments. For years, we've seen this in this wonderful Hubble Space Telescope false color image of the Veil Nebula. The colors are not realistic, but the structure is, and you can see the whole structure exactly as in the diagram. The helix around the outside, the straight line towards the center, and filaments breaking down into smaller filaments or larger filaments built up out of large ones. From JWST, we have this contribution. People have already said it's highly hypnotic. This is a nearby galaxy, M74, face on. And through the infrared, we see the same structure of filaments inside filaments, a fractal structure forming the skeleton of this galaxy along which the stars are forming. This occurs at all scales. This is our fusion plasmas inside our small dense plasma focused device. These same filaments occurring at centimeter scales. This is star forming filaments at parsec scales. This is a very recent radio telescope image of a nearby cluster of galaxies showing these long twisting filaments, a pair of filaments. And for scale, this letter E would be almost exactly the same size as the Milky Way. So if you put the Milky Way in these filaments, these would be filaments capable of leading to the formation of the Milky Way galaxy. Because what's happening is a third process, the homopolar generator, Faraday disk generator process, discovered by Faraday, in which if you have a rotating conductor in a magnetic field, such as a rotating disk of gas inside one of these filaments, you produce an electric potential between the outside and the inside towards the axis, and current starts to flow perpendicular. And since the current can't flow perpendicular to the field, the current actually creates its own magnetic field, its own vortices, so it can flow along these filaments that we see in spiral galaxies. So basically what's happening is a large vortex breaks down gravitation along its axis. So where angular momentum doesn't fight gravity because it's breaking down along the axis. And then these spinning blobs get their own set of spiral filaments to carry current from the outside to the inside of each of these smaller elements, which, depending on the scale, might be a cluster of galaxies, a galaxy, star cluster, an individual star. 30 years ago, my colleague Tony Peratt made these supercomputer simulations, starting with two blobs of plasma, presumably condensed by gravity, in a magnetic field, which would be perpendicular to the plane of the image. And within 2 rotations, by magnetic forces and electrical forces alone, because gravity isn't built into this model, they form a striking spiral galaxy with many of the quantitative features we see in real spiral galaxies. Back again in 30 years ago, I used these models to show what plasma physics could tell us about the formation of a galaxy and the formation of stars in the galaxy. The model predicted that larger stars, but not supernova size, basically up to 10 times the mass of our sun, would form first. They would be very bright stars forming lots of helium, and through cosmic rays, both deuterium and lithium would form, and the amount of these elements would be formed in the amounts that we actually observe in young galaxies. So all of these light elements would be formed through the action of galaxies that would be formed by plasma processes that we can understand here in the lab. The prediction that young galaxies were forming helium at an extremely high rate relative to their mass was borne out by the later discovery of the ultraluminous IR galaxies, which are forming helium at a rate per unit mass about 100 to 1,000 times that of the present Milky Way. It's been long known that the energy that must have been generated by the formation of a quarter of the helium in the universe, which is a quarter of the mass of hydrogen being converted into helium, by some strange coincidence, produced the amount of energy that we now observe in the cosmic microwave background. We know that energy was thermalized by dust in early galaxies to about 20 K. How was it thermalized further to 2.7 K? Well, again, we go back to plasma phenomena. There's one more plasma phenomenon that we have observed in the lab, and we can now extrapolate to the universe, which is the production of plasmoids. What happens when you have converging filaments they tend to merge together, twist together, and then they start to kink like an old landline of a telephone. And it kinks and it sort of twists on its side and forms a tiny plasmoid, which is kinked up in all three dimensions. We've observed these plasmoids in the lab, and back in the 1980s, I hypothesized that these are at the core of phenomena like quasars and Herbig-Haro objects. These plasmoids in the lab decay rapidly and produce beams of highly accelerated electrons and ions. This is an artist's conception of our plasmoid in the lab. This is a real picture of a similar beam produced at much greater scale by a quasar. These beams have to create a hierarchical filament of very dense magnetic vortex filaments. The electrons trapped in these filaments, which survive for billions or tens of billions of years, scatter light at microwave and radio frequency radiation, not at shorter radiation wavelength. So these filaments created by quasars, AGN, and other phenomena create a radio fog, which thermalizes and smooths the CMB to the situation that we now observe. I published these theories again 30 years ago, Astrophysical Journal and so on. The evidence that we live in a microwave fog is, if you look out into a fog, the light that is scattered by a fog obviously dims faster than 1 over r squared. And if we look at nearby galaxies, we find that the radioluminosity goes down much faster than the IR luminosity. And this is at distances 100, 200, 300 megaparsecs that are far too small for there to be significant evolution. So this is clear proof that we're living in a radio fog, not an opaque radio fog, but a radio fog that does produce the CMB. So in these many papers we have published, and especially in these two big ones, we see that all cosmic processes can be explained with lab-tested physics, except the Hubble process. You ask me what causes the Hubble process, I will say, I don't know. But what is clear from the work that I and Ricardo and Renato have done, that the universe is not expanding. That means that the redshift has to be caused by something that happens to the light as it travels these long distances. And we know pretty exactly what the formula is, because its redshift is proportional to distance. Now, the good thing about this is we can study that experimentally. If we put up satellites that have sufficiently sensitive instruments within present day technology, we can study this at distances of millions of kilometers in the solar system. And hopefully we will in the coming decade or so. Well, what does all this have to do with us? It's not just cosmology that's in crisis. Humanity's in crisis. And this crisis has been obvious since the beginning of the pandemic, but it doesn't date back just to the pandemic. This graph shows the evolution of energy growth and the evolution of mortality decline in the human race since the Second World War. And what we see is things were getting pretty rapidly better. The rate of mortality decline was very rapid back in the good old 60s. And so was the rate of energy growth. In the decades that followed, both of those growth rates declined, and we entered a period of near stagnation, which was partially broken by the entry of China into the world economy in the first decades of the 21st century. Now these curves have turned sharply downward. We are definitely in a period of retreat and decline. How long that period lasts is determined by what we do now. To get out of this crisis, we need to do many things. But one of the things we absolutely need to do is to get more energy. We need more energy, cheaper energy. I don't think I have to persuade people of that these days. Cleaner energy and high energy density. So we are not using billions of tons of fuel as we are today to get our energy. To make a long story short, the only way we can do that, we can fulfill those four needs, is with fusion energy, the power that drives the stars, the power of the sun, the power that drives the universe. To get control of the power that drives the universe, we have to understand the processes that drive cosmic evolution. Just like the Wright brothers needed to understand how birds fly to create a controllable flying machine, we have to understand these phenomena to create fusion devices that work. In tokamaks, which are the dominant device, these filaments are uncontrolled and they lead to disruption. They can even destroy the machine itself. In our device, a different kind of device, which has been around for a long time, called the dense plasma focus, we use these filaments to create the conditions for fusion. Let's see whether this works. So what happens is filaments are created by a pulse of electricity stored in capacitors that moves through these quite small electrodes. The electrodes are centimeters across and naturally forms these filaments, which become to start to heat up. And they move through their own forces to the end of the anode, which is that central cylinder. They pinch together and they kink into this tiny plasmoid. Obviously, of course, this is animation by Torov Greek, was the first to show exactly how those plasmoids could form. Plasmoids heat up to, we have measured 260 keV, 200 times the temperature in the center of the sun. And they can be used to burn PB11 fuel, which forms pure helium as an end product. So we've seen these filaments in ICCD exposures. This is a 5 nanosecond exposure. And we've seen the plasmoids, which are, as I say, quite tiny in our experiments on Earth. Where we are going with these experiments using hydrogen boron fuel is to develop generators that would fit in a garage and develop enough power to fuel 4,000 American homes. So that's one connection. There's a second connection, which is to overcome the crisis, we have to win humanity as a whole to rationality, to the scientific method. We have seen all over the world people dying needlessly. In our country, we have had over 1 million deaths, 90% more avoidable deaths, primarily because people do not judge correctly scientific findings, such as about the validity of vaccines. As Alfvén wrote 40 years ago, the Big Bang has caused science to become increasingly presented as the negation of common sense. The line between science and pseudoscience tended to be erased. And it was difficult to tell the difference between science and science fiction. If you present as the highest popular incarnation of science as the Big Bang Theory, cosmologists as the smartest scientists, the priesthood, and you say, okay, believe inflation, the Big Bang, dark energy, dark matter. Oh, my colleagues have a vaccine to present you. It is undercutting the credibility of science, and that has to be reversed. We have to say the science of the cosmos is based on the same principles that have given us technology on Earth. The same technology that allows technological miracles like the JWST is the science we have to use for the cosmos, not something concocted on in a computer or on a blackboard. And finally, the third point, and then we'll open it up for the discussion for the rest of the time. Cosmic evolution, as we look at it through the lens of plasma physics, is running up. What we see is a process of large-scale structures developed over not billions, but trillions of years, leading to higher and higher energy flows on smaller and smaller scales of both time and space. A tendency for increased energy flows, for motion away from equilibrium, that we know, at least on Earth, has continued through the evolution of life. That cosmology as evolution is contradicted by the Big Bang cosmology as degeneration. In the Big Bang cosmology, the universe started with high energy flows and is degenerating over the billion years to a grim future of heat death, dispersion, meaninglessness, nothingness. In crises that humanity has faced, our greatest enemy is despair. If you look back to the great crises of the earliest 20th century, the Great Depression, ideologies of despair, such as fascism, developed out of people losing hope that society could get better. That loss of hope was fed by ideologies that said, yes, evolution is running backwards, the Earth is running down, society is decaying, the cosmos is running down, and therefore we have no choice but the devil take the hindmost. The core of fascism is society cannot benefit together. It has to be a competition of the strongest versus the weakest, and you better be a member of the strongest. We face that again, and science, in reality, correctly understood, can say, yes, again and again, not only has humanity gone through crises, such as the Depression, such as the Dark Ages, and come out of it stronger at a higher level, greater energy flows, but so has the universe. So has life itself. This is part of a general process of evolution. Whether the ideology of hope or the ideology of despair wins is really up to us. Which comes to my last slide. Instead of many of the things on the internet you'll see end with a word from their sponsor, well, we're going to end with a word to our sponsors, which is you. All of this research that I'm doing is funded by members of the public. We're funded by crowdfunding, in which people invest, yes, in the hope that we will succeed or their investment will be worth money, but mainly to help us develop fusion. And in the process, we're funding the basic research in cosmology that helps us to develop fusion. So I hope some of you will visit WeFunder and maybe see fit to chip in your $200. Thank you very much, and we'll spend the rest of the time in discussion. So questions, comments? Just unmute yourself. We have
This is
we have 50
Tony Black
people
speaking.
here,
Is
which is
my
good, but
volume
it's not too
appropriate?
many. Go ahead.
All right. I have a few questions. One concerns the large-scale inhomogeneities of the universe. Could they be described within a plasma cosmology framework that fits within the Big Bang time framework, or is that not possible?
No. In other words, when we look out into the universe, we can use spectroscopy to allow us to tell how fast objects in the universe are moving. So if we look at, for example, a single galaxy, we'll see one side of the galaxy has a redshift which is slightly less than the center of the galaxy. One side has a redshift which is slightly more. So we can see that the galaxy is spinning at, let's say, 200 kilometers a second. If we look at larger scales, clusters of galaxies, superclusters, we get up to maybe 1,000, sometimes as much as 2,000 kilometers a second. We never see things faster. And oddly enough, this is the fastest we see plasmas going in our experiments here on Earth. And Hannes Alfvén and his colleague, Dr. Falthammer, they proposed, among other things, they discovered, among other things, that in plasmas, velocity tends to be scale invariant. So velocities here on Earth tend to be the same as we see in the universe, which means the larger an object is, the slower its evolution. So we can see that since objects don't move any faster than about 1/1000th, or at worst 1/300th the speed of light, objects that are billions of light years across must have taken hundreds of billions or even trillions of years to develop. So there's no possibility that inhomogeneities on the scale that we've already been observing can be created within a Big Bang context. That's why even Joseph Selk, he didn't expect these to be discovered when he made this statement in '88, but he said it would be a clear contradiction. You have at these scales objects that are far older than 14 billion years, orders of magnitude.
I have a further question. What's your view on the recent alleged photos or pictures of the black holes? Professor Pierre Robitaille is of the opinion that they're just statistical artifacts, but could they be plasmoids?
Yes. We have on our website, and people should visit our YouTube channel, which is LPP Fusion on YouTube, and also our website, which is lppfusion.com. We have a lot of additional materials. We did a series of 4 short videos on the first Horizon Telescope images of, now I'm blanking, M87. And M87, it certainly was consistent with a plasmoid viewed, as they agree, fairly near its axis. And there are reasons to believe that M87 is pointing in our direction. One of the things that distinguishes a plasmoid from these black holes is that a plasmoid, although it has extremely high velocity plasma, the plasma is moving about 10,000 kilometers per second. In a black hole, the plasma should be moving approximately 300,000 kilometers a second, close to the speed of light. You do not see plasma moving that quickly in these objects, which is probably a giveaway that they are not black holes. The one at the center of our galaxy is, frankly, to my mind, more perplexing. I'm perplexed for the same reason they are. Why is it pointing towards us? It doesn't look the way you would think an object like this would look side on, either from a black hole standpoint or a plasmoid standpoint. But we're in the plane of the galaxy. It's clear that most of the filaments coming out of the object at the center of the galaxy, Sagittarius A, are going up along its axis. So it does make you a little suspicious of the analysis. I personally cannot judge the analysis. The analysis does involve a great deal of mathematical work, not because it's a dim object, but because it's very difficult to get an image of an object which is changing on a very short time scale. So I guess I'll be agnostic for this time on what the best explanation of our Sagittarius A is. The observations fit M87 pretty well as a plasmoid.
One more question, if I may, then I'll leave it to
Sure.
the rest.
And then we have to move on to people who haven't asked.
Right. How does your work interface with Halton Arp's work, in your opinion?
Well, I knew Chip Arp, and Chip was a terrific hero. He unfortunately became our Galileo because he was actually pretty much forced into exile by being thrown off of, he was an observer and he was thrown off of all the big telescopes, had to move to Germany. His observations are extremely interesting, and he discovered a lot of great things about galaxies, including how they interact. But I don't think that as a theorist, he was as outstanding as an observer. And I don't think he would have claimed to be either. I think his theory of aging mass had a lot of holes in it, because he was saying that mass was actually changing over time, and atoms were getting heavier. And the problem is that we measure atoms to very high degrees of precision, and there's no mix. I mean, an oxygen atom and another oxygen atom weigh exactly the same. If there were oxygen atoms of different masses because they were different ages, all the turbulence in the galaxy would have mixed them. And as our sun condensed out of this mixture, we would have a mixture of ages and therefore masses. And we just don't see that. As I say, I don't think that you need changes in mass or anything like that to explain the phenomenon in the universe. The steady state theory was an expanding universe theory. And I think our work and other works have demonstrated that the universe is not expanding. So you don't have to explain how to fill it up. Okay, somebody else who hasn't asked a question so far. Or a comment.
Hi, Eric.
Hello, can anybody?
Sorry.
Okay, Gerald and then Mark. Two of you spoke at once. Gerald. Gerald Black, you were speaking? You have to unmute yourself. Unmute yourself.
Yeah, I wasn't actually speaking, but I do have a question. One of the arguments for dark matter is that the rate that stars revolve around the galaxy doesn't conform with, what gravity says they should be revolving about. And that means you have to have dark matter, supposedly. So how would you explain that in light of, this plasma theory?
Well, you might get two answers from myself and Ricardo. Just a second. Let me go back to sharing the screen. Okay. It is clear that magnetic fields can control plasma. And if we look at the outer skirts of the galaxies, where these flat rotation curves start to contradict the idea that they are being controlled by the mass that we observe, magnetic fields are very important. We are measuring the motion of plasma by the radio waves this plasma is emitting. And what I and other researchers developed and published is that the magnetic fields that we observe out in the outskirts of the galaxy can control these plasma masses. So what we are seeing is not the control by gravitational, but the control by magnetic fields. Now that produces a clear prediction, which is the stars themselves are so dense that the magnetic fields don't have a big impact on them. Their inertia sort of barrels through the magnetic fields. So if the stars are being controlled mainly by gravitation, we will see a slower motion of the stars far out in the galaxy and a faster motion of the gas. So this is what this image is showing. The top image is the measured motion of the plasma in the Milky Way galaxy. And the bottom image is showing the velocity of the stars. So as we move outward, we get very high velocities, 300 kilometers per second for the plasma, but the bulk of the stars are moving a great deal slower. There are some rapid stars, which may be leaving the galaxy, but most of them are down around 200, 150. So I actually don't think that you need anything other than magnetic fields to explain these rotation, either at the scale of galaxies or even clusters of galaxies. But I think Ricardo would have a different answer. Is that true? Ricardo may no longer be with us. It's getting pretty late in Spain. All right, well, Mark, did you have a question?
Yes, I was wondering, you can hear me okay?
Yes.
Great. I was wondering about the question of the redshift, because the Einsteinians always claim that the redshift is due to the stretching of space, which is essentially nonsense because space-time and matter are all infinite. But my point is that the redshift would then be entirely due to merely mutual repulsion between matter, and that the further you move out in space, the further the redshift, and at a distance where galaxies are receding from us as fast as light, that would be, I would presume, the Hubble distance, and beyond that, galaxies are receding from us faster than light, but we are generally unable to see them. Would that sound a reasonable proposition?
Well, let me put it this way. An explanation of the Hubble relationship in a non-expanding universe, you have to develop some new physics. You cannot, as far as I can see, and I've read a lot of explanations, you cannot explain it by any known phenomena of the interaction of radiation with matter, for the simple reason that there isn't enough matter out there. There are quite a few plasma phenomena that can create a redshift, but they require thousands of times more matter than we see in the universe. So, or to put it another way, if this was the cause of the Hubble, if any of these phenomena were the cause of the Hubble relationship, the Hubble distance would be thousands of times bigger because the effects are just too small. So I think you are looking at some fundamental process that modifies the laws of electromagnetism that causes photons to steadily lose energy. Now, what this process is unknown and will have to be studied as we put these instruments out into the solar system so we can measure these effects precisely. But as Paul Dirac noted, again, a century ago, it is curious that if you compare atomic scales, such as the classical radius of the electron, 10 to the minus 13 centimeters, with the scale of the Hubble distance, the ratio of those scales is roughly, not exactly, this ratio of the electric force to the gravitational force. So maybe this decay has something to do with the linkage between the electromagnetic and gravitational forces. But we have to say this is pure speculation until we can develop a theory that develops new quantitative predictions. We already know that the Hubble relation is a linear relationship. We can't go back. We can explain that, but we can't use that as a new prediction. We have to develop some quantitative prediction, such as the magnitude of the Hubble constant, and a rigorous theory that can go beyond our present physics in explaining this phenomenon. So I think that that's going to be the work of quite a long time. It's not going to happen tomorrow. But we're going to need new physics for this one phenomenon. We're still way ahead because we've gotten rid of new physics for the Big Bang itself, which is an effect without a cause. So we get rid of that. We get rid of inflationary field. We get rid of dark energy. We get rid of dark matter. And one thing that I didn't mention, we get rid of baryon non-conservation, because in the Big Bang, you would get equal amounts of matter and antimatter, and they would so thoroughly annihilate each other that the amount of matter left over would be 100 billion times less than what we see around us. So the Big Bangers have to hypothesize some supersymmetry force that causes protons to decay and causes matter to be slightly better than antimatter, none of which we observe. So all of that we would throw away too. We would accept the results of trillions of experiments in our accelerators that whenever matter is created, antimatter is created in exactly equal amounts. And in a universe that was never simultaneously hot and dense, Hannes Alfvén explained decades ago that the interaction of magnetism and gravitation will push matter and antimatter apart so that you end up with all matter superclusters of galaxies and all matter antimatter superclusters of galaxies, and very little interaction between them at extremely large scales. Okay. Another question?
Can I ask another question?
Well, let's first ask if there's somebody who hasn't asked a question who wants to ask the first question.
Good idea.
Yeah. Douglas, are you trying to get on?
I was, yeah. I asked a question earlier, but if somebody else
all
has
right.
got
Well,
a
is there a
question.
new person? There are 50 of you
Not
out
new.
there. Don't be bashful. Or 40 still left. We're losing some people as it gets later. By the way, this is being recorded, as you've all been informed, and we will put it on YouTube in a matter of days. So people who, this was in the wrong time zone from them will be able to chip in then. All right, one last call for people who have never asked questions. All right, well then, Douglas, you can ask another question.
It's not really a question, and I hate to
Go
go
ahead.
back to the redshift again, but it's something I've thought about for many, many years. And it's kind of, I know people hate thought experiments, but if you look down at a light ray end on all the way to the source, it's a really long light ray, especially if you're going back to galaxies. Now, if you've got a really long light ray, if you could almost take the equivalent energy of that light ray and work out what the equivalent mass of that is, could that mass stretch the redshift? In other words, at the longer the light ray, the more equivalent mass based on the equivalent energy. Could the equivalent mass stretch that redshift more and more the more the distance goes? Because that would explain any redshift if you're looking at any galaxy or supercluster to great distances. The equivalent mass wouldn't have to be that great to stretch that light ray.
Well, but a light ray itself is not a real thing.
I'm just throwing that out there.
Yeah, a light ray is not a real thing. I mean, what is real is a little complicated, and I'm not saying we understand it totally. What is real is light waves spreading outward from a source, just like a ripple, quite analogous to a ripple on a pond, and photons. Now, quantum mechanics says quite a bit about how photons relate to light waves. It doesn't explain it entirely because it doesn't explain how photons come into existence and go out of existence. It's a phenomenon we observe all the time. But light rays are just a convenient geometric way of describing the path that light takes. Just like, when you're traveling and you have the phone in front of you and it shows your path, that path is not real. It just traces a series of locations that you've been on the road. Well, a light ray is the same thing. It's not real. It traces a series of locations that a given photon or a given part of the wavefront would take. So there's no reality to the light ray, so it can't have mass, it can't have energy. It is certainly true that, something, if you have an isolated photon that does not interact with an atom or with plasma, as it travels over large distances, it is related to a wavefront that is astronomical. right? In other words, if you have a supernova explosion that blows up at time Z, a billion years later, the light from that supernova will have a wavefront that is 2 billion light years across. And we know from quantum mechanics that there is some relationship among all the photons in that light wave. So, obviously there's room for, at the moment, speculation. In the future, maybe theorizing of saying, oh, can we relate this delocalization of the wavefront to the fact that the light is losing energy? Maybe. I mean, as I say, it's suggestive that if you take, what I'm saying now is mathematically true. It's not saying anything about physics. If light is losing energy according to the linear redshift, and every oscillation of a photon, it loses energy equivalent to a photon whose wavelength is equal to the Hubble length. So these are very, very tiny energy photons with extremely long wavelength. So the quantum relationship is the longer the wavelength, the smaller the energy. So if you can relate the Hubble length somehow to the strength of gravity, which is also something like 10 to the 40th magnitudes, 10 to the 40th times less than the strength of the electromagnetic force, which is the force that controls the photons as they move through space, electromagnetic wave, then you're getting somewhere. The problem is you have to do it in a way that's right. And getting quantitative predictions that are exact to the extreme degree that we've measured these quantities is very difficult. I can tell from experience, 40 years ago, I tried to do it myself. And it's easy to convince yourself, oh, you have a theory that predicts something. But then when they discover the next decimal point or the next 2 decimal points, your theory is wrong. So this really has to be a completely different direction for a lot of experimental and theoretical work. To crack these problems, we're not going to have to go, to our blackboard or whiteboard and draw equations or go to our computers to make up simulations. We need an experimental and theoretical program using both plasma experiments in the laboratory, experiments in our big laboratory in the space, in the solar system, and measurements out into space to get a handle on this new physics. And if we could reorient the funding that has been funding people to study imaginary things like Big Bang, dark matter, dark energy inflation, then we'd have a lot of really clever scientists working on these problems. But they would have to reorient from what could be called the Ptolemaic, pure mathematics attitude towards science, that we can derive what the universe is like by making the best equations, to the experimental approach to science, which is we have to relate what we see in the cosmos to what we can do in our experiments here on Earth and within the solar system. Long answer to short question. Okay, go ahead. Anybody who has spoken can ask additional. We still have 10 more minutes.
I've got one. I've got one. Maybe it's just a teaching point. I'm used to the general relativistic shift being related to matter, right? But do you add in the magnetic energy to that? Does the magnetic energy in these great distances in the cosmos also produce a redshift? Not just the
Well,
matter.
this goes to this inhomogeneity thing. Let's take a step back. General relativity. It's sometimes said, oh, the Big Bang is a consequence of general relativity. Well, no, it's not. General relativity predicts a Big Bang if you add in one big assumption, which is that the universe is homogeneous at the largest scales. Well, we've been observing the universe for a century since Einstein's work and Lemaitre. We've never observed a scale in which the universe is homogeneous. The universe is fractal. It's inhomogeneous at all scales, which means the density of the universe depends on the scale that it's measured. The larger the scale you measure the density, the lower the density is measured. So that means that on the scales that we're already observing, the density of matter is so low that the curvature of space is negligible.
Okay.
So the amount of matter in the universe is very small compared with the amount of matter that would be necessary to curve it on Hubble distances. Well, if you look at the energy in the universe is actually quite small compared with the amount of matter. So we all know, we remember that energy and matter can be converted into each other. So an average, a proton, all protons contain 1 GeV of energy, approximately 1 billion electron volts. The energy in the cosmic microwave background is about 4 MeV per proton, 4 million electron volts. So it's a factor of 250 times smaller. The energy in the magnetic fields, in the kinetic energy, all of those are down around hundreds of thousands of times smaller. Because as they say, galaxies and so on move at about 1/300th the speed of light. You square that to get the energy. The energy is down by hundreds of thousands. So all the energy in the universe is small compared with all the matter in the universe. And all of that matter makes only, a 1% difference in general relativistic terms. On large scale,
Right, thank you.
Newtonian physics is a good approximation.
Thank you.
Okay, well, we have time for one more question before we wind up.
I have a question.
Douglas, yes, other Douglas, Walt, yes.
Yes, sir. I just wanted to know if you had any thoughts or comments on a big government ITER fusion project, and maybe how that was, I don't know, different or the same as what LPP is doing. I know they've been in the news a little bit lately.
Right. Not very favorably, unfortunately. I'll say two things about it. The general comment is more than 40 years ago, the governments of the world made a decision to put all their eggs,
Yes.
fusion energy eggs, in the tokamak basket. Tokamak, people who are not familiar, is a type of fusion energy device, one type among many. There were many bureaucratic and political reasons for doing that. One of the strongest was in the United States, the energy crisis was at its peak. This was the early 70s. The scientists wanted to say this was a near-term thing. This was an engineering project like the recently completed Apollo project. Unfortunately, that was untrue. To a certain extent, it was a lie because the physicists knew it wasn't true. To a certain extent, they convinced themselves it was true, and therefore it was an inadvertent misstatement. But it wasn't true. It was a scientific research project. Nobody knew then, and nobody knows now what the best device is. You won't know until it happens. Nobody's produced more energy out of a device, even in the laboratory, than they put into it. We're all still trying. So it was wrong to make that decision. The tokamak has big disadvantages because it uses very low density plasma. If you have low density plasma, you have to confine it for a lot of revolutions to give them the fusion process a chance to complete. And that means it has to be absolutely stable. And that's really impossible. You're asking the impossible. So I don't think these devices will ever work, the tokamaks. ITER has additional problems because you joke about, what was it? The giraffe is something created by a committee or something insulting to giraffes. Well, this was a project that was politically designed to have everybody do everything. All parts were made repetitively in different countries. So instead of like the JWST, where the Europeans said, hey, we're going to make this instrument, and all we have to do is know where this instrument is going to come and plug into your giant telescope. And as a result, they actually spent the money that was needed. They ran it in the correct method. They divvied up the work, and you have a technological triumph. ITER is exactly the opposite. You have everybody making the same parts, and parts that were made in other parts of the world and are carried, great distances. These huge parts, bigger than any of the dwellings we're in, have to be fit together to sub-millimeter precision. It's impossible. It's a crazy way of doing it. And right now, the holdup is the French government, in inspecting it, said, hey, these parts won't fit together. It's not safe to put them together because they might fall apart. So this is big government at its worst. We see that this is not a necessary effect. The government could have run a great fusion energy program if they had said, we need to fund everybody. This is a crash program. We need to get it done. Everybody gets funded. If you do it right, you can end up with a result like JWST. If you do it wrong, you get ITER. Okay, well, listen, it's been fun. And this is just the first stage of the discussion post JWST. I think I'll be participating in some discussions in Europe and in the coming months, and hopefully we'll finally break through the censorship and get this debate rolling. Thanks everybody for coming. Please do visit WeFunder and tell all your friends about this debate and about fusion energy. Thanks. Take care all.
Accelerating advanced fusion energy.